Good afternoon, everyone. The topic of today's lecture is molecular orbitals and hybridization. Now, in order to learn about hybridization, which is in your syllabus, you have to know something about atomic orbitals and molecular orbitals. So, what are molecular orbitals, or in fact, what is an orbital? An orbital is the space where the electrons are most likely to be found. This much you know. Now, when two atomic orbitals combine, they will form an equal number of molecular orbitals. Okay? Now see, these are the two atomic orbitals of hydrogen. One is orbitals of hydrogen. They contain the valence electrons. In fact, hydrogen has got only a single electron, which is the valence electron, and that is in fact which is most important electrons of the atom or the molecule, whatever it is. The atomic orbitals, when they overlap, they will combine to form molecular orbitals as follows. Like this. The overlap of two 1s atomic orbitals results in the formation of a sigma molecular orbital. Okay? This molecular orbital is of course much more stable than the individual atomic orbitals from which they are formed. Obviously, otherwise the molecule will not exist. Now the sigma bonds, this is the covalent bond formed between the two atoms when end-on overlap of orbitals occur. This we know from definition. So the molecular orbitals encompass the whole molecule. Okay, and it is not concentrated between the two atoms inside the molecule. It actually encompasses the whole molecule. And this is the diagram showing that the formed molecular orbital has got a lower energy than the individual atomic orbitals. Like these are the atomic orbitals of individual hydrogen atom. They have come together, they have combined to form molecular orbitals. Two molecular orbitals, as I said earlier, when two atomic orbitals combine, they will form two molecular orbitals, one of which is more stable than the individual atomic orbitals, and the other one is less stable, that is more energetic than the individual atomic orbitals. Now the one which is more stable will house the two electrons forming the bond. That is the sigma bond, and such an orbital is known as the bonding molecular orbital. This is the sigma bond represented in an energy diagram. Now the shape of the molecular orbitals will be governed by the overlapping atomic orbitals and the type of intermolecular bonding that is observed. Now the molecular orbital formed from overlapping of the atomic orbital is of course always symmetrical around the midpoint where the bonding electrons are most likely to be found. The shape must always be symmetrical. Okay, now after we get a concept of atomic orbitals and molecular orbital, we come to the concept of hybridization. First and foremost, what is hybridization? Hybridization is a concept of mixing of different types of orbitals. For example, mixing of two atomic orbitals resulting in two molecular orbitals, which will now be known as hybrid orbitals. Now, why such a mixing is required? Why do we have to bring in this concept? We all know the ground state electronic configuration of carbon is 1s2, 2s2 and 2p2. But we also know that the valency of carbon is 4. So if there are two unpaired electrons, how come there are 4 bonds? We have to have 4 unpaired electrons to form 4 bonds. So in order to explain such anomaly in nature, the concept of hybridization had to be invoked. How does it work? First we have to look into the shapes of the different atomic orbitals. S orbitals are spherical and the p orbitals are double shaped. Okay, fine. Then we have the hybridization theory, which assumes that the electrons of the 2s orbital, because I told in the beginning that only the valence electrons need to be involved. So 1s orbital we will not look into. The electrons of the 2s and 2p orbitals of carbon mix together and form 4 degenerate orbitals. What do you mean by degenerate orbitals? When the 4 atomic orbitals mix, they result in 4 molecular orbitals or hybrid orbitals, and each of such orbital is of equal energy. Okay? All the orbitals are of equal energy. The mixing takes place in this fashion. We have got 2 electrons in the 2s orbital and 1 electron each in individual px and py orbitals, and the pz orbital is empty. What happens? 1 electron from the 2s orbital is energized and it goes into the 2p orbitals, mixed together, and the ultimate result are 4 hybridized orbitals, each of equal energy. See, the 2s orbital had a lower energy, that is more stable than the 2p orbital, but after mixing, all the hybrid orbitals are of equal energy. Now, since such orbitals have resulted due to the mixing of 1s and 3p orbitals, they have been named as sp3 hybrid orbitals. Okay. Now, the shape of the 2s orbital was spherical. The shape of the 3p orbitals were double-shaped. So, after mixing, they hybridized. Because you see 90-degree angle is shown because each of the px, py and pz orbitals are orthogonal to each other. So after the mixing of s and 3p orbitals, they will be hybridized to form hybrid orbitals which have got more of a double-shaped nature in them and less of spherical, because there are 3 p orbitals combining and they have a shape of a dumbbell. Now obviously, since all the 4 hybrid orbitals are of equal energy, and each will house an electron, so they have to be oriented in such a fashion that there is minimum repulsion between each of the hybrid orbitals, and we have to have an acclaimed geometrical shape to give that orientation, and that geometrical shape is tetrahedron. If the 4 hybrid orbitals occupy or are directed towards the 4 corners of a regular tetrahedron, then both the conditions are satisfied. The fact of their having equal energy and the fact that there is minimum repulsion between the electrons, that is, each hybrid orbital has got 1 electron, so there will be minimum repulsion between the electrons in each hybrid orbital. The sp3 orbitals formed are all half-filled. We know that the maximum capacity of each orbital is 2. They can house up to a maximum of 2 electrons. So, since each hybrid orbital has got only 1 electron, they are all half-filled, and the electrons are more likely to be found in the larger lobe. In fact, when we draw or when we give a pictorial representation, we usually omit the smaller lobe. We use the larger lobes to represent the hybrid orbitals. See, we can discern a familiar tetrahedral shape, and the angle is maximum to minimize the repulsion. The angle between each hybrid orbitals being 109 degrees 20 minutes. Now, how can this hybridization help to give an insight into the shapes of different hydrocarbons? Let's start with alkanes. In methane, all the 4 hybrid orbitals are used to form sigma bonds between the central carbon atom and the hydrogen, because we know that the formula for methane is CH4, that is, a single carbon is bonded with 4 hydrogen atoms. In ethane also, a similar type of bonding takes place where each of the 4 hybrid orbitals are used to form sigma bonds with 3 electrons and the adjacent carbon atom respectively. See, this is the sigma bond where one hybrid orbital, one sp3 hybrid orbital from each of the 2 carbons participate in end-on overlap, forming a sigma bond having free rotation around the bond. Okay, this much we knew. We got an idea about the single bonded compounds or compounds where pi bonds don't exist. So how can we explain the formation of pi bonds or double bonds in alkenes? As with alkanes, here also the bonding is due to hybridization. The electrons from the 2s shell is promoted to an empty 2p orbital, like this. So what happens? In the first step, see, we are taking only 3 orbitals, that is 1 2s and 2 2p orbital. The third 2p orbital remains empty. Okay, and it houses a single electron. Sorry, it doesn't remain empty, it houses a single electron, but it remains unhybridized. So we have got hybridization by mixing of one s and 2p orbitals, resulting in sp2 hybridization. The fourth orbital remains unhybridized as a pz orbital. Okay. Now these 3 sp2 hybrid orbitals obviously has to have an orientation to minimize electronic repulsion, and the best possible orientation is a planar orientation with an angle of 120 degrees between them. These are the 3 sp hybrid orbitals, and this is the unhybridized pz orbital standing out. Now we have another carbon having a similar sp2 hybridization, and the 2 sp2 hybrid orbitals from 2 different carbons overlap, forming a sigma bond. The other 2 hybrid orbitals will form sigma bonds with the 1s orbital of hydrogens, and we have got the pz orbital, one on each carbon atom, which is unhybridized. As we can see that the 2 pz orbitals are parallel to each other, and this parallel orientation allows the formation of a pi bond. Because we know that a pi bond is formed by lateral overlap of 2 orbitals. So if these 2 orbitals overlap laterally, a pi bond results. Okay, the p orbitals of the carbons are always parallel and close enough for sideways overlap, resulting in a pi bond. Okay, in this pi bond, the electrons are not concentrated at a particular place, but they are moving around the pi bond, and this is the representation of a pi orbital. Now let us consider about a triple bond. What happens in case of triple bond? In triple bond, like acetylene, one s orbital and one p orbital combine to form sp hybrid orbital. Since 2 orbitals combine, the resulting hybrid orbitals are also 2 in number. sp, 50% s, 50% p, but the sp hybridizations, hybrid orbitals, they have a shape like this, but we will consider only the larger orbitals like this. So after hybridization, you can see that 2 p orbitals remain unhybridized, and 1 p orbital has hybridized with 1 s orbital, forming 2 sp hybrid orbitals. And these unhybridized p orbitals, see, there are 2 unhybridized p orbitals, this one and this one, and each p orbital is perpendicular to each other. So the py orbital of one carbon is parallel to the py orbital of the other carbon. They will overlap sideways, forming a pi bond, and the pz orbital of one carbon will be parallel to the pz orbital of the other carbon, and they will overlap sideways, forming the second pi bond. So in all, we have got, and of course the sigma bond is formed by the overlap of sp hybrid orbitals on each single carbon. So we have got a triple bonded molecule. Now let us look at a summary. If it is a single CC bond, it has got one sigma bond with a bond length of 154 picometer or 1.54 angstrom. If we have a carbon-carbon double bond, it comprises of a single bond and a pi bond, having a bond length of 1.34 angstrom. And if we have a triple bond, it comprises of a single bond and two pi bonds, a sigma bond and two pi bonds, having a bond length of 1.21 angstrom. Now, looking at the bond length, we can see that though the double bonds are stronger than single bonds, but the value is not double. They are not twice as strong as the sigma bond. The reason being, a sigma bond, because it is formed by end-on overlap, is much stronger than a pi bond, which is formed by lateral overlap. Much more energy is required to break a single bond compared to the pi bond. So in general, since a pi bond is weaker than a sigma bond, so the bond dissociation energy or the bond length, anything, will not be twice that of a sigma bond, because both the bonds are not of equal energy. If they had been of equal energy, the value would have been twice. But since they are not of equal energy, the value is less than twice. This is a summary of the shape of the molecules. And a molecule having sp hybrid orbital is linear in shape, because that is the best position to minimize repulsion between the electrons, having a bond angle of 180 degrees. And sp2 hybrid orbital has got a planar or a trigonal planar shape, having a bond angle of 120 degrees. And an sp3 hybrid orbital will have a tetrahedral orientation with a bond angle of 105 degrees, 28 minutes. These are examples of certain compounds and the hybridization they have along with the bond angles. Now let us look into aromatic hydrocarbons. Best example is that of a benzene. We have heard that benzene contains delocalized electron. Now what is the meaning of the term delocalized? The meaning of the term you can get from hybridization theory. Initially, this was the structure of benzene drawn by chemists. You see the double bonds are static over here. But we have seen in a number of chemical properties as well as physical properties like bond length or addition reaction, the double bonds in benzene are not static. They tend to be dynamic. So, this structure does not hold good for benzene. So what happens? Each carbon atom of benzene, now we use the hybridization concept. Each carbon atom of benzene has got at least one double bond. So we invoke sp2 hybridization for the molecule. Now since each carbon atom has got 3 sp2 hybrid orbitals, one with hydrogen and the two with the other two adjacent carbons, the remaining unhybridized p orbital forming the pi bond. It is not involved in rigid bonding, so each carbon atom of the benzene can be represented like this, with an unhybridized p orbital for each of the carbon atoms. So we can see that all the p orbitals are parallel to each other. As a result, there is a chance of lateral overlap among all the orbitals, and this is what actually takes place. A planar molecule with all the unhybridized p orbitals parallel to each other above and below the plate, resulting in a delocalized bi-molecular orbital both above as well as below the plate. Now that is what is meant by delocalized orbital. And this is what we have in mind when we draw the structure of a benzene ring with a circle inside it. The circle represents that the electrons, each single electron in each of the unhybridized pi orbital has got the capacity to delocalize or move about the whole ring. That is what is known as delocalization, which solves a lot of problems like the single observed bond length for benzene, and not two different bond lengths, one double and one single, but a mean value of the two, because all the bonds are, you see, similar over here. Single bond and a pi localized electron. So this explains the structure of benzene ring. So thanks for today, and this is the end of my talk.